Hi everyone, I am Rohit from Group 5. Today I want to talk about our group project, which is improving the paper Deep Differentiable Logic Gate Networks. So first of all, let me give you a brief background on why are we focusing on logic gate network. Logic gate network is inspired by logic circuit design. When we translate a neural network to hardware, there is no inductive bias. During that, there is no matrix multiplication, no weight in that network. It is very important for hardware inference on FPGA and ASIC, where model is already converted into logic, which can run really fast for inferencing. So what are logic gates? As you can see on the right, these are the truth tables for logic gates like AND, OR, XOR, NAND, etc. In logic gate network, we have number of logic gates at each layer. The idea is throughout the network, we learn the optimal choice and combination of various types of logic gates. This not only improves the performance but also interpretability in neural network. In this example, we train the logic gate network to classify if the picture is of giant panda or red panda. Now my teammate Johnny will explain about differentiable logic gate network.
So what the differentiable logic gate network? So author give the two idea about and he's using relaxations. The first is revalue logic. For me, it's pretty straightforward, right? And it's just and he give you an example for and a nut. Long story short is you see the top right hand side and relax A and B. For example, A multiply B, A and B within that 0 and 1. Same logic when the not relax A, right? Say A is within that 0 and 1 as well. So the long story short, so the value will discrete it into 0 and 1. However, this operation on differentiable, which is to pose a problem in the neural network if we rely on the gradient-based optimization, especially happen on the backward propagations. So the author gave the idea about the probability distributions, which is the relaxations over the choice of the logic gates. The example is underneath, right? As we give the two input computer values under the propagation distributions. And for this example, we find the best one. We give the thumb up, and because we have a computational for 0.19. So how's that works in the neural network? We split the images into the 0 and 1 with the smaller slide and get the two input throughout the logic gate network and eventually throughout the forward passing and the backward propagation, pick the randomly distributions, find the best logic gate to replace that. And throughout the process in the iteration one by one, eventually build a network, and then finally do the classification, decide it is a giant panda.
Now I will explain how I have tried to improve the paper. So let's look at what's really interesting here. This graph tells quite a story about our model improvements. When we started with our baseline model, shown in blue, we were getting about 50% accuracy on MNIST. Not terrible, but definitely not where we wanted to be. You can see it learns quickly at first, but then just plateaus around epoch 150 and actually starts declining after epoch 300. What really transformed our results was reimagining the architecture. Our baseline was pretty simple, just two logic layers with a moderate neuron count and a standard atom optimizer. It was basically hitting a ceiling. The improved model, shown in red, is where things get exciting. We went from 2 to 6 logic layers, added ReLU activations at each layer for nonlinearity, and dramatically scaled up the neurons from 392 to 8000. We also switched to Adam W optimizer with custom hyperparameter tuning. Look at what happens around epoch 150. The red line crosses the blue and just keeps climbing. By epoch 250, we have hit 80% accuracy and continue improving to nearly 90% by the end. That's a significant improvement. This wasn't just about throwing more compute at the problem. The combination of deeper architecture, nonlinearity from the ReLU layers, and better hyperparameter optimization solved the fundamental limitation of our baseline approach. And notice how the improved model keeps learning without any signs of overfitting, unlike the baseline, which either plateaus or actually gets worse over time. This case really demonstrates how architectural choices can make or break performance, even on a relatively simple dataset like MNIST. Now Johnny will present how he has improved the baseline architecture of the paper, which is actually very interesting.
We try the two data set means and the subaltern. And the top left-hand side, you can see we try data aggregation, phase one and two warm up. They're all working good for the means data set. Furthermore, we try the CN at the front end. However, you can see it's showing good in the beginning. And if you see the left bottom side, but if I move further to see more APOC, and it turns out you see from 3 to 10. For after the 3, you will see the accuracy is actually not improving, stay still. And I'm wondering why it's not improving significantly. So for my personal, I did more detail about how to do the CD LGN, which is convolution front end on the differentiable logic gate network. So this is the improving I have. The first improving is using the logic or pooling instead of original pooling in the CN. So this is the idea for or. You can see the table the one items, Boolean item there. Most likely they are one except for or equal to zero. So very straightforward. Leverage the idea for the logic, and I can find a close to one, which is higher. This is the max matrix, very similar with the max pooling. Eventually find a zero point 0.9. The second is most important improving I have is add a softmax binary logic tree. This is the second improving. Long story short, it's this is just for the gate selection original from random right now is determined by the probability. Because this is softmax, like each gate learn the mutual of the Boolean operations. But because each gate only processes two input at a time, the binary tree structures using the hierarchy combine many features. In other words, the tree organizes this pairwise decisions so that simple learned binary operation can be composed into complex overall decisions. This hierarchy design, which is from the tree, defeating Boolean logic, and able to the network to capture the pattern by the successful merge to the output of each gate. In the third, improving is resilient initiations, right? So the remaining the gate values. So how should we design it? Actually, uh, rather than using the original from the author, is a standard Gaussian initiation. This is the initiator parallelism for resilience via the one particular logic gate, often the feed forwarding gate. The 4 and the 5 in my invention is most likely for whole neural network. The first one is warm up. I have a 50 APOC and the warm up learning rate is from 8, from 1 to 8. After that, I just let the formal learning rate keep going. And also add the middle and the later freeze and unfreeze. The idea is about to let the network gradually absorb and consolidate what has been learned. The last one is data parallelizations. Basically, I using Python data distribution parallelism, Python DDT to leverage the multi GPU to run faster. This is the result I have. As you can see, the yellow is baseline, red is the improved model, which is CD LGN. The right hand side tables had the statics numbers with all more detail analyzed in here. In general, the result you can see is around like a 10% higher than the baseline. So this is the result I have. In general, like I say, it's 10% higher, but you see the oscillations happening here. So if we move back to this diagram, you see the red dashed line. This line chart have some deep drop up the accuracy during the trainings. So this is definitely we need to resolve that by the hyperparameter tunings. But in general, I think it's a meaningful improving for the real world because we see the ultimate, the final accuracy. It's actually fitting the real world usages. If I have the time, I would like to try further, which is in original differential logic gate network module provided by author. It's pretty old, using very old CUDA modules and with the old Pythons. So it's not compatible with if I want to build the binary tree. So I have to build my own basically reference the original author to build my own Python modules. So I want to go back to fix and to be able to upgrade the CUDA to the most updated versions aligned with the Pythons. Second, like I say, we need to do more hyperparameter tuning to resolve oscillations. Last one is because of time limit, I haven't had the time to try the inferencing. I definitely want to try to improve that. This is my presentation. Thank you.
Hi everyone. Today I'll be presenting my work on implementing and improving differentiable logic gate networks. This project explores an interesting intersection between neural networks and logical reasoning, attempting to build models that can learn through differentiable approximations of logical operations. So to talk about my approach, when attempting to implement the architecture described in the original paper, I faced a significant challenge. The official diff logic library was inaccessible to me due to my resources constraints. So, and also instead of relying on my teammates for my approach for the project, which is difficult because each needed to concentrate on its part of the project. So I created a custom implementation of the core components, the logic layer and groups and classes. This workaround aimed to approximate the same logical operations using principles from fuzzy logic, all within a differentiable framework. This is like to talk about the custom architecture components. My implementation centers around two key components. First, the logic layer, which replaces traditional activation functions with differentiable versions of logical operations. Specifically, like the AND, OR, and NOT gates, each operation process inputs through separate channels and then combines their contributions using learnable weights. I implemented temperature parameters to control the sharpness of these operations and mechanisms to balance their influence. The second component, the group sum, serves as a classification layer. So unlike traditional approaches that apply, for example, softmax across all outputs, group sum divides the features into groups, then applies softmax within each group, and then aggregates the results. This structure goal is to produce more interpretable probability distribution. For the baseline implementations, I created like a custom one. So I tested this architecture on the Cypher 10 image database using a standard training approach with a stochastic gradient descent optimization and a cosine learning rate schedule for around like 50 epochs. The baseline results were low. My custom implementation achieved a best accuracy of only 10.48%, just barely above the random guessing at 10%, that is like 10% for each class. This suggested that while my approach concept was interesting, the current implementation wasn't effectively learning from image data. For my improvement efforts to address these limitations, I've implemented several improvements to both the architecture and training processes. Architecturally speaking, I added like residual connections to improve gradient flow, layer normalizations to stabilize training, and then adaptive mechanisms to better balance the logical operations. On the training side, I incorporated advanced data augmentation techniques, including mix-up, which blends like pair of images and their labels and cutout that which randomly mask regions of input images. And I also extended the training to 100 epochs to give the model more time to learn more complex patterns. These are like the performance visualizations. This first one is for the baseline, custom baseline. So we can see the baseline shows accuracy fluctuating narrowly, like around 10% for over like for around 50 epochs with minimal learning process and progress. So the improved version, despite running for 100 epochs, which is this one right here, and incorporating like additional techniques, still struggles to meaningful exceed random chance performance. We also observed like an increased volatility in the accuracy measurement, suggesting potential issues with the learning rate or optimization process. As analysis of limitations, I think several factors contribute to this performance limitation. First, the architecture treats images as flat vectors, discarding the spatial relationship that, for example, convolutional networks naturally preserve. And second, I think the aggressive dimension reduction path might be losing too much information. And also the group sum implementation might not be effectively like separating class probabilities. And finally, I think the hyperparameter configuration also seems to be quite sensitive. And as evidence of that, we have the oscillating validation accuracy. For conclusion and also future directions, I think several modifications could improve this approach for image classification. For example, integrating convolutional layers before the logic layer would be better to capture spatial information. This is similar to what Johnny did for his improvement. And also simplifying the architecture could help isolate potential issues. More careful toning also of the learning rate might reduce this volatility. And alternately, I think this approach might prove more effective on structured data problems rather than using it. Are also like hybrid architectures where, for example, yeah, convolutional features can be like fed into logic layers. Also for conclusions, I think while my implementation didn't achieve competitive performance on Cypher 10, the core concept of integrating differential logic operations into neural networks remain very valuable. So this experiment conducted with the access to the original library demonstrates that, for example, these techniques can be adapted for alternative models. Even if performance is currently limited, as we see, it provides me like with a foundation in logic based deep learning classifiers, since I needed to look for like a not like a black box implementation. So I think I gained like a very good foundation on these logic-based deep classifiers. And also, for example, for applications where decision transparency is very important, this kind of approach where you can see exactly what is happening within the classes is very valuable. Thank you so much for your attention.